Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum. Welcome to the first lecture of week 6. So in the last week, we have discussed chapter number 19, that is bulk deformation process. And in that chapter, until now, we have discussed forging operation, rolling operation, and extrusion. So we were left with some practical problem, numerical problem for the extrusion. Then we will move towards the final type of the bulk deformation process, that is the wire and the bar drawing. So let's start with this numerical problem. It states a billet that is fed in the extrusion container that is 75 millimeter long and 25 millimeter in diameter is to be extruded in a direct extrusion. So we have the direct extrusion here. We have a container with some dies at certain angle, and it has a billet. It has a billet inside. Right. So it's a direct extrusion, so it is being pressurized from this direction, and it will extrude out from this one. So it says a billet that has a 25 millimeter diameter. This diameter would be 25, and this length would be 75 millimeter. Okay. In a direct extrusion operation with the extrusion ratio, that is Rx equals to 4, the extrude rate, the thing which has been extruded from here, the extruded has a round cross section, so we have the round opening of the orifice. The die angle, that is a half angle, is equals to 90 degree, so we know that is equals to 90 degree. The work metal has a strength coefficient of 415, so that is a strength coefficient equals to 415 megapascals, and the strain hardening exponent of 0.18, that is 0.18. Use the Johnson's formula with A equals to 0 and B equals to 1.5 to estimate the extrusion strain. Now what it says, determine the pressure applied to the end of the blade as the ram move forward. We have to identify the pressure that is being applied. If you remember the formula for the pressure in the direct extrusion, when you take into consideration the friction also, the complete expression for the pressure was P equals to YF, that is the average flow stress, into extrusion strain plus 2L by D naught. 2L by D naught. So this is the length. Any instantaneous length? It's at any instant, and we have the D naught, that is the initial diameter of the billet. So that is the total pressure that is used, that is applied in the direct extrusion. So let's start with it. First and foremost, we will find out the strain. We have the ratio, the extrusion ratio, so we'll just directly determine the strain. The true strain in this case was equals to ln of Rx, so that is equals to ln 4.0, so that would be equals to 1.3863. so this is the value of the true strain. Right, then we have to find out the extrusion strain, that is based on the Johnson's formula. So the extrusion strain would be equals to A plus B ln of Rx, or we can write it as A plus B into true strain. So that would be equals to A is 0.8 plus B is 1.5 into 1.3863. So the extrusion strain would be equals to 2.8795. So as we know, now we have the extrusion strain, we have to find out the flow stress, and we have discussed that the flow stress will be based on the true strain. So the flow stress here would be equals to, as it's the average flow stress, so that is equals to flow curve into true strain exponent strain hardening divided by 1 plus strain hardening. So we have the flow curve equals to 415 into the true strain is equals to 1.3863 exponent the strain hardening exponent, and that is equal to 0.18. So we have 0.18 divided by 1 plus 0.18. So if we solve this one, it would be equals to 373 megapascal. This is the value of the flow curve, the flow stress, and we have the value of the extrusion strain here. So we have this factor. Now we have found out this one. We know the L and the D naught. So it says the pressure applied to the end of the billet. So the initial length was 75 millimeter. We can select the intermediate length. Let's say we have extruded some amount of the length of the billet. Now the remaining is the 50 millimeter. Now we have extruded some more amount. The remaining in the container is 25 millimeter, and last the theoretical value, that is 0 millimeter. Although in reality it won't happen, because we have studied that even towards the end of the extrusion operation, there will be some amount of material left within the container, and that is known as butt. If you see the initial discussion of the extrusion process, so we have to find out the pressure at each of these length. So we have P equals to YF, that is 373, into the extrusion strain, that is 2.879 plus 2 into 75 by 25. So you can find out the initial length. So that would be equals to 3312 megapascals at L equals to 75. You can again find out at L equals to, let's say, 50. So it would be again equal to 373 into 2.879 plus 2 into 50 by 25. So it would be equals to 2566 megapascals. This is how we can calculate the pressure along the whole extrusion process. So towards the end of the process, we have L equals to 0. So we can have 373 into 2.879 plus 2 into 0 by 25. So obviously, as I said before, theoretically, practically it's not possible. We are just finding it out theoretically, so we will have the value equals to, that is 1074 megapascals. So we have 1074 megapascals towards the end of the process. So although for the direct extrusion this is not possible, but for the indirect one, this would be the pressure that is required if this process was performed indirectly. Obviously, as we know that in direct extrusion there is no relative motion between the work part and the container, so there is no friction that is present there. So that's why this value can be considered as the uniform pressure that is required to perform the indirect extrusion. So that's all for the extrusion process. Now we will move towards the Next and the last type of the bulk deformation process, that is the wire and the bar drawing. So what is the wire and the bar drawing? The first and foremost, it's the type of the bulk deformation process, and in this type of the process, the cross section of a bar, rod, or the wire is reduced. So the primary purpose is just reduce the cross section, either the bar, rod, or the wire, by pulling it through the die. So here it is being performed through a pulling action. There is a tensile forces involved. While in all the other cases of the bulk deformation, or the other cases of the bulk deformation, either in the rolling operation or in the forging or in the extrusion, we have the compressive forces that are involved here. But in the case of the wire and the bar drawing, we have the tensile forces involved here, right? So it is similar to extrusion. The basic scheme is like similar to extrusion. We have a container, we have a die. This hole is a die surface, and there's a work billet or a work stock, and that is being pulled, that is being passed through this die opening. But the only difference is in the extrusion the force is being applied here, while in the case of the wire and the bar drawing, force is being applied, it is being pulled. In the extrusion it is being pushed, right? That is the only difference between the extrusion and the wire bar drawing. Although drawing applies tensile stresses, but there is a compression that plays a significant role, because when metal passes through this die opening, there is a compression in the metal when passing through this die. So it's not like it's a completely tensile mode, although the force that is being applied is a tensile in nature, but the compression also plays a vital role when performing the wire and the bar drawing operation. So that is a basic schematic. So here we have the working stock or the starting stock, the work material. In the case of the extrusion, we call that billet. We have a dies. If as you know, in the extrusion process we have a container that had some die cavity like this one in the case of the extrusion process, right? So in the drawing we have directly die cavities. We have the final stock with some change cross section, with some change diameter here, and there are regions within the die cavity which we will see in the next few slides. So let's move towards certain advantages and disadvantages. We will not go into much detail of this wire and the bar drawing. Okay. So the advantage of the drawing, it has a good dimensional control, like in the case of the extrusion process, because we have the metallic dies, we are capable to produce close tolerance. Because of this good dimensional control, we have a good surface finish as well. There's enhanced mechanical properties such as strength and hardness, and why is that? So again, due to strain hardening. And I expect you to know what the strain hardening is, because we have discussed this time and again in this whole chapter. In every process, strain hardening has a vital role to play. Drawing speed can be as high as 50 meters per second, so it can be a very high speed process as well. But that's not always the case. In the case of fine wires, we can have speed up to this. Otherwise, it's at least slower than this one. So these are certain advantages for the drawing operation. What is the difference between the wire and the bar drawing? In the previous process, we have only one name, either rolling or the forging or the extrusion. But in this case, we have two names for the same process, wire and the bar drawing. So because there is a certain difference between them based on the machine and based on some parameters, although the basic process is same. So the difference between is that the bar is somewhat a large diameter stock with a larger diameter, either bar or the rod, while if we call it a wire, we have a small diameter, such as it ranges down to 0.03 millimeter. So if you have a smaller diameter, we call it to be a wire drawing. If you have a larger diameter stock, we call it to bar drawing. And because of this change in diameter, we have a change in the machines that are used for these two processes. As it says, the mechanics are the same, The method, equipment, even terminologies are different for this one. Although they both have same pulling mechanism from the die opening, but the machines that are involved here and some other terms that are used to understand this process are different. So what are the drawing practices? It is usually performed as a cold working operation. In the previous processes, like in the rolling, forging, and extrusion, they can be performed in both ways, the hot working and the cold working, because our primary concern was both, either to change the significantly plastically deform that material or cause significant shape change, or we can have a purpose of increasing the strength of the material. But in the case of the drawing, there is not much change in the dimensions, although we do change, but it's not so big. So that's why it is mostly performed as the cold working operation. So we get the increase in strength as an advantage of the drawing process, and it is mostly used for the round cross sections. Common products, our electrical wires that are manufactured using the drawing operation, rail tracks in the railways, that is also made from the drawing operation. We have certain bar stocks which are further machined and forged to get the final products. Springs that are used, the rivets, they all are some examples for the drawing operation. So what actually the bar drawing is, we will first go through the bar drawing, then we'll move towards the wire drawing. So in the case of the bar drawing, it is accomplished as a single draft operation. You know what the draft was? In the case of, as you know, remember, in the case of the rolling, the draft was initial thickness minus the final thickness. It means that whatever we achieve in a single pass, that's how we used to find out the draft initially, to find out the capability of our mill. So draft was whatever we are achieving or changing the dimension in a single pass. So it is performed as a single draft operation, means the bar drawing will always have a single pass. It will pass only one time, that's it. The stock is pulled through one die opening. So we have a one die, uh, and we have a bar, and there's a carriage that is pulling this bar using some hydraulic system, and the bar is being pulled through this die opening only once. So that is what is called as a single draft operation. So the beginning stock has a larger diameter and is a straight cylinder, as you can see here. So this basic scheme of the bar drawing necessitates the batch type product operation. As you know, the batch type operation, when we make a batch of same dimension products, some, like we make 1,000 bars of same dimension in length, so this type of it necessitates a batch type production. So if you see this bar drawing table, we have the entry table, this one. We have a carriage that is pulling, it is pulling the stock. Behind this carriage we have a hydraulic system that is powering this carriage. We have the drawbars, our work material. We have the die stand which contains the dies, and this is the die. And there is some, here at this point, there is some lubrication also, right? At the entry side, not at this point, toward this entry side, when it's entering into the die cavity, there is some lubrication as well, right? So this is the basic scheme for the bar drawing operation. If you see the wire drawing, it has a slight change because it's a wire drawing. So that was a single draft operation, it is only performed in a single go, while the wire drawing is a continuous drawing operation, that we have a long you can stock of the wires, and that is being continuously deformed in the drawing operation. So that is called the continuous drawing. It is being performed continuously, consisting of a multiple draw die. So we don't have a single die like in the case of the bar drawing. We have a single wire is passing to first die, then it is again passing to second die, and so on and so forth. So we progressively reduce the diameter of the wire drawing of the wires, because in the case of the wire drawing we have to achieve a very small diameter. So we don't do it all at once, we do it progressively, passing through first die, and then the second die, and so on and so forth, based on our requirement. So we have multiple draw dice. Typically it range from 4 to 12. So these draw dice might range from 4 or to up to 12. So, and these dice, they are separated by accumulating drums that are known as the capstan drum. So these die pairs are separated by this accumulating drums which are accumulating the wire. So the name of this accumulating drum is the capstan drum, right? So what is the purpose of the capstan drum? The first, as we can see here, that it is holding the wire, it is storing the wire, so we can have the continuous supply of the wire. And second one is that you might assume that okay, we can have a single drum to store a wire. Why we have a capstan drum after each draw die? The purpose is that it's not only storing the wire for continuous supply, it is also keeping it in a stretched position, so that the wire should be stretched always. It shouldn't be like wire is going like this, right? So it should always be stretched and straight, so there is no distortion in the while performing the drawing operation, right? Then we have, as you can see here, before this die cavity, this is our dice reduction in diameter. Before this die, the wire is passing through this lubricant, so it is being lubricated before entering into the die region. So each die provides a small reduction, so desired total reduction is achieved by the series of dies. As we have already discussed, we have series of dies, so they progressively reduce the diameter of the wire. There is a process that is called annealing. So the annealing is sometimes required between the dies. So there might be a chance that between two dies there is an annealing process. What is annealing? Annealing is a heat treatment process. If you remember, we have discussed briefly in the first chapter, in the beginning of our subject, that there is a process called the heat treatment process, and the purpose of the heat treatment process is to not to change the shape but to change the properties. So what annealing particularly is, annealing is a softening process. It is a softening process. So we perform the annealing between the two dies so that our wire becomes soft and it can be easily deformed, right? So it heats the material up to recrystallization temperature, and you know what the recrystallization temperature is. So it heats the material up to that temperature and allow it to cool down in the air, in the open air, without any external medium like water or some other source. So we allow it to cool down in the air. So that's called the annealing operation. The purpose is to soften the material so that it can be easily deformed in this way. So now we know the difference between the bar and the wire drawing. Bar drawing is a single batch operation, while the wire drawing is a continuous drawing operation. In the bar drawing, the material is passed through a single die, while in the case of the wire drawing, we have multiple dies that range from 4 to 12. So, and we have another feature here that's called the accumulating capstan drum, which accumulate the wire and also keep the wire in the stretch form, in the tension, so that there is no distortion here. And we perform the annealing before the wire drawing operation, or in between the dies also. So these were some differences between the wire and the bar drawing. So let's jump towards certain features of the die cavity itself. If we closely observe the die cavity, we have certain region. The first one is the entry region. What it does, it funnels the lubricant into die cavity, as we have seen in the previous figure. We have a lubricant, you can see the pink one, we have the lubricant before this die cavity. So the purpose of the entry region here, it funnels the lubricant into the die cavity so it can flow into the die cavity. Then we have the approach region, the longest one. It's a cone shaped region where drawing actually occurs. So this approach region is mainly responsible for reducing the diameter of the wire or the bar. Then we have the back relief region, right, we have the back relief region. So back relief region is the exit zone, so provide with a back relief angle of about 30 degrees. So this angle is about 30 degrees, so that if there's a spring back phenomenon, means as you know, the metals are elastic in nature, so once they are deformed they try to regain its shape. So this provides a relief, it provides some space for metal to regain its shape, to expand again. Then there's another area that's called the bearing surface. This region that's called the bearing surface. So bearing surface determines the final diameter. It determines the final diameter or the final dimensions, you can say. So these are certain features of the draw dies. So before performing the drawing operation, there is a preparation of work. That is, we prepare the material before the dyeing operation. The first one is the annealing, as we have already discussed. The purpose of the annealing is to increase ductility or to soften the material. Then we have cleaning to prevent damage to work surface and draw dies. So we clean the surface of the dies as well as the work part, so there are no oxides on the surface that end up damaging the surface of the material or the die. And the pointing, as we know, the die or the wire is like flat from the beginning, so we create some pointed surface like this one. So once we have the die region like this one, so these draw dies can be these wire or the bar can be easily fed into the die cavity. If we have like this one, so it will stuck here, so we create a pointed so that once it passes here, then this can be caught by the carriage and pull it, right, as we have seen in the previous slides of the wire drawing in this one. So we simply make it pointed from the beginning and we insert into the die cavity so that carriage can easily hold that and apply the tensile force or pull it through the die cavity. Last, we have a short analysis for the wire and the bar drawing operation. So as we know, it's a reduction process, so we have certain parameters in the drawing operation. The first and foremost is the reduction ratio. We have the reduction ratio, that is equals to initial area minus final area divided by the initial area, right? And obviously we mean the cross section area here. Then we have the draft. We had the draft in the rolling operation also, we had the draft in the drawing operation also. That is, in the rolling operation, that was equals to initial thickness minus final thickness, because we were reducing thickness in that operation. In this operation we are reducing the diameter, so we have the initial diameter minus the final diameter. So this is the draft. Again we have the extrusion here, the strain here. The value of strain would be equals to natural log of initial area divided by the final cross section area, and based on this strain, the stress required would be equals to flow stress into the strain. So that flow stress, and it will be the average flow stress, because there is no impact load involved in the drawing operation, rather we are applying the pressure or the force over the long period of time. So we have the YF into ln of E naught by AF. So we won't go into much details for the drawing operation, we will just stick to here. You know how to calculate the strain, how to calculate the draft and the reduction ratio. Then towards the end of the chapter, there are some specialized drawing operation that is known as the tube drawing. So the purpose of the tube drawing is not only to reduce the diameter of the hollow tubes, but also to control the wall thickness, here. So it can be used to directly reduce the diameter like this, but to control the inner or wall thickness, especially for the seamless pipes and tubes, so we can have a thing called the mandrel, as you can see here, the mandrel, and another thing is called the plug. So they both are used when we not only want to reduce the diameter, but we also want to control the wall thickness. So what is a mandrel? Mandrel is a supported metallic plug, you can say. So we can have it in between the die at the bearing surface of the die. So the remaining opening would be the thickness of the tube. So this is how we can reduce the thickness of the tube, whatever we want to reduce. So but what if we have the very long pipe, so we cannot have a very long support for the mandrel. So for that we enter a floating plug into the pipe. So once this plug gets stuck into this bearing surface, so the remaining opening would be the the thickness of the wall. So this is how we can reduce the thickness of the wall, by using a floating plug for the longer pipe, floating plug for long pipe tube. We can have the mandrel for pipes and tubes, right? So these are two specialized operation for the drawing operation. So that's all for the bulk deformation process, and it's also the end of the chapter number 19. In this chapter we have discussed the rolling, we perform analysis and the numerical problems, we discuss the forging and its types, and the extrusion, as well as the wire and the bar drawing. So in the coming live session, I will try to make a chart for you to summarize all these four processes in a single page, so that you can easily remember each and every aspect of the process. So in the next lecture we will be starting chapter number 20, that is a second type of metal forming process, that is sheet metal process. Assalamu alaikum.